I draw a picture of a positive charge, a positive producer, it's got an electric field that surrounds it. Which way does that electric field point? Outward, right? Good, away from the positive charge. If I draw a negative producer, remember with gravitational fields, you only got one kind of producer, but with the electric fields, you've got two, the positive and the negative. If I draw a negative producer, which way does the field lines point surrounding it? Inward, towards it, right? Where does that come from? Where does that direction of the electric field come from? How do we define the direction of the electric field? Kristen? Good. Good. We don't have a positive particle in the field right now, but if we were to put one in that field, it would move away from the first diagram and toward the second one. So that means the field should be away from it in the first one and toward it in the second one. Let's draw that little positive in there. Okay, it goes to the right in diagram number 1. It goes to the left in diagram number 2. You can see that it's the direction of the electric field. Good. What if I was to put a negative particle in there now? Got a little negative particle in there, got a little negative particle in there. Which way is it going to move in the first diagram? It's going to move inwards, right? It's going to experience a force toward the producer. And this one's going to experience a force away from the producer, right? Does that change the direction of the electric field? What's the difference between a positive field and a negative field? It's a bit of a trick question. There's no such thing as a positive field and a negative field. An electric field is a field. An electric field is an electric field. The direction of that electric field is always based on which way a positive would go when placed in that field. A negative will always experience a force opposite to the direction of the field. So positive with the field, negative against the field. Let's draw an electric field here. One simple random electric field line drawn this way. Let's put a positive in there. Let's put a negative in there. Let's label A, B, C, and D. In that electric field, which way will that positive particle experience the force? Towards A, B, C, or D? It will experience the force towards D. Positives will always experience the direction of the force in the direction of the field. Okay, it's going to go towards D. Which way is the negative going to go? Which way is the force on that little negative particle, that electron or whatever it is? A, B, C, or D? A. Right? The negative particles always experience a force opposite to the direction of the field, so it's going to go towards A. Good. What's the difference between a force and a field? There's always a field as long as there's a producer. There's sometimes a field when there's a producer as well, but not always. In order to have a field, all you need is something to cause it. In order to have a force, which is defined as a push or a pull, you need something to be pushed or pulled. You need to have an experiencer. So to have a field, you just need a producer. To have a force, you need a producer and you need an experiencer. That's why we introduced the idea of fields. Sometimes you've got this influence, but there's nothing there being influenced. There's nothing to be pushed or pulled. So you've got to have some way of describing that it's still there. There's still electricity there, even though there's nothing experiencing it. That's what a field describes for us. The electricity that's there, even when there's no object to experience that field. All right, we introduced two equations yesterday. Or a couple of days ago, I should say. E is equal to kq over r squared, and then we had E is equal to f over q. The first equation we call the blank equation. Starts with a P. Yeah, it's the producer equation, good. And the second one is called the experiencer equation. When you have information about what causes the field, let's use the first one. When you have information about what experiences it, let's use the second one. Q in the first one stands for what? What does this stand for? Q, charge of the producer. This Q stands for? Good, the charge of the experiencer. Now, if you know what the variables are, you know the charge you have is the charge of the producer or the experiencer or whatever it is, and so on and so on and so on, then these questions tend to be pretty easy, right? You know you've got data for the producer. Use the producer equation, plug it in, and solve it. But sometimes it's a little bit difficult to tell whether you have a producer or whether you have an experiencer. Sometimes you gotta read between the lines a little bit. Here's a general rule of thumb. If you're trying to find the field strength where the charge is, then that charge is probably experiencing the field. If you're trying to find the field strength somewhere other than where the charge is, then it's probably producing it. For example, here's a charge. I want to find the field strength over there. Is that field strength caused by that positive charge, or is it experienced by that positive charge? No, it's caused by. You can't experience something if you're not there to experience it. That's the rule, right? You can't experience it if you're not there to experience it. I think the analogy we gave yesterday was the hockey game, right? And the atmosphere at the hockey game. Okay, in order to experience the atmosphere at a hockey game, you need to be at the hockey game. In order to experience the field right here, this charge needs to be right there. It isn't. It's not an experiencer. What does it got to be? A producer, right? So if it's at the point where you're trying to find the field or where you have the value of the field, it's going to be an experiencer. If it's somewhere other than a certain distance away from where you're trying to find the field, then it's going to be a producer. Generally, if you have a distance given to you, it's a producer. Read it closely just to make sure, but usually if you have that distance, it's going to be a producer. Let's take a look at the questions that you had on 550 for homework last night. Any issues with 1 and 2 on that page? Dylan? 2? 2? Okay. Number 2 says an electron and a proton are this far apart, 5.29 times 10 to the minus 11 meters, in a hydrogen atom. Determine the net electric field at a point midway between these two charges. Let's draw the picture. Hey, I don't know how many people still today have been calculating or trying to calculate a net force or a net field or something without drawing a picture. Okay, one person just in the last class put his hand up and said, can you help me with this? And I went over there and I saw a little bit of math, but I saw no picture. And I said, no, I can't help you with it. I've been telling you guys for days, draw the picture. It helps. Draw the picture. Hey, trust me. Draw the picture. I might know what I'm talking about. Here's the proton, here's the electron. The proton has a charge of positive 1.60 times 10 to the minus 19 coulombs, and the electron has a charge of negative 1.6. They are 5.29 times 10 to the minus 11 meters apart, and we want to find the field strength right there, midway in between these two charges. We got to draw a diagram, and we're not finished with this diagram yet. Okay, we've drawn what I call a situational diagram. We need all of the fields in this diagram as well. There are two fields, the one caused by the proton and the one caused by the electron. The field caused by the proton is going to go to the right. We'll call that EP for the electric field by the proton. It goes to the right because it goes away from a positive producer, away from the proton. The field caused by the electron is also going to go to the right. Can anybody explain to me why the field caused by the electron is also to the right? Field lines always point which way? Away from positive and toward the negative. So both fields are going to be to the right. First one is away from the positive, the second one is toward the negative, but they end up being both to the right. So let's calculate both of those fields now. The electric field caused by the proton, it is a producer here because this field strength is not where the proton is. Okay, in order for that proton to experience the field, the proton has to be where the field is. It's not. So let's use the producer equation. EP is equal to KQ over R squared. And the distance, what would the distance be here? Yeah, half of it, good. Sometimes we've got to divide it in two, sometimes we don't. It just depends upon the situation. Don't just automatically say, oh, it's R, we divide it by 2 because it's radius. It's not radius. Radius is of a circle. This isn't a circle. Okay, it's a distance. It just happens to have the same symbol as radius. And this distance happens to be cut in half because the distance we're given is twice what we really need. But it doesn't always happen that way. What is that R? 5.29 divided by 2. 2.645, thank you, times 10 to the minus 11 meters. And we can't forget to square that. Probably the most common mistake. This morning on the quiz, period 2, somebody, as I was walking around taking a look at what they were doing on the quiz as they were writing it, I saw somebody put in big letters at the top of their quiz, "Don't forget to square." Okay, I think that's great when somebody writes something like that. Okay, if you think you have any chance at all of forgetting to square that R, and lots of you will forget to square it at some point, then make that note on a quiz or a test. We do the math here. I think we're going to get something like 2.05, 2.055, 2.056 times 10 to the 11 newtons per coulomb. Now we're going to calculate the field caused by the electron. Anybody see how I got that number so quick? I didn't just calculate this in my head, right? 8.99 times 1.6 divided by 2.645. What did I do in my head? What's the value of this field caused by the electron going to be? It's the same numbers, right? 1.6 times 10 to the minus 19, 2.645. It's going to be the same value, right? So how did I get it? I looked at the answer over there and I divided by 2. Right? I know that they're both in the same direction, so I know that the field caused by the proton has to be half of the overall field. So let's add them up now. The net electric field is proton plus the electron, giving me 4.11 times 10 to the 12 newtons per coulomb. Now what about the direction? Well, we've got it drawn as a right-left thing, but the question doesn't actually say which one's on the right and which one's on the left. So we don't want to say to the right. We want to say it's 4.11 toward the electron. Or we could say 4.11 away from the proton. Is that good? You guys feel comfortable with that? Yes? All right, let's take a look at the check and reflect questions that we had for homework as well. Those check and reflect questions were on page 553. All right, what do we got to do for 553, 1 through 9? 2, 9b, that seems to be a pretty common one, actually, 9b. 5, 6c, 8b. Going once, going twice. Sold. 2, 5, 6c, 8b, and 9b. 2 says, why was it necessary to introduce the idea of field theory? Well, understand that field theory is a human-made idea. There is no such thing as a field per se. There's not lines. If you look above the Earth, you never see lines pointing toward the Earth. Or if you look outside of a charge, you never see lines pointing toward or away from that charge. We needed something to describe what was happening, even when there was nothing there experiencing it. Justine asked a question a few minutes ago about the difference between a force and a field. I told her that the Earth's gravitational field is there, is right where she is, whether she's there or not. If she stands up and takes her desk with her, then the field is still there. It's caused by the Earth, it's still there. But the force isn't. If we just described gravity in terms of a force, as soon as Justina walks away, we have no way to describe gravity because there's nothing there to experience it, so there's therefore no force. If we introduce the idea of fields, then we still have a way to describe gravity even after Justina has got up and walked away. So we introduced the idea of fields essentially so that we have a way of describing what's going on when we have nothing there that's experiencing the field. Okay, does that make sense? Question 5. If vector arrows, I should say, can represent an electric field at point starting a charge, identify 2 ways that the vector arrows shown below represent differences in the electric fields around 2 source charges. So we've got one around this negative producer and then one surrounding this positive producer. What are 2 differences between these electric field lines? Don't overanalyze this. Don't make it harder than it has to be. Really, this is a question where sometimes we just look at it and we're looking for a really complicated answer. But in the end, we end up overlooking the simple answer. The way the proton's moving? Yeah, basically, the direction. The direction of the field is different. That's one of the differences. The way a proton would move if placed in the field is different. The direction of the field is different. The first one is to the left. The second one is diagonally up and to the right. Good. So direction is one. What's the thing that often goes with the direction? Magnitude. The magnitude's different. Which one's a bigger field? How do you know which one's a bigger field? Size of the arrow. Sometimes we don't know what the field strength is when we're drawing a diagram, so we can't indicate which one's bigger. That's okay. But if we do know which one's bigger, then we should indicate roughly to scale which one's bigger, which one's smaller. The one on the left here is bigger, so that means the field strength is going to be larger as well. The one on the right is smaller, so the field strength is going to be weaker. So direction and magnitude, those are the two big differences there. That's it. Next question we had was 6C. This is one of those variable value changing questions, right? C says, describe the effect on the electric field at a point if the magnitude of the test charge in the field is halved. The test charge is the experiencer. So we're reducing the charge of the experiencer by half. What effect does it have on the electric field? Well, my original electric field is F over Q. I'm going to use my experiencer equation because we're talking about what happens on the electric field if the magnitude of the experiencer is cut in half. Oh, this is actually... Somebody check the back of your book. I want to see what they have. Anybody have a copy of the book? I want to see what they have because the way that I was about to do this question would actually give us the wrong answer. And I want to see if they have done that. I have a feeling, a sneaky feeling, that they've done that, giving us the wrong answer there. Just check that, Jordan, okay? Okay, the answer's not there in the back of the book, apparently. Here's what I was going to do. I want somebody to explain to me when I do it why it's not correct. Okay? The original field is F over Q. If I cut the test charge of the experiencer in half, my new field would be equal to F over, what's it going to be? 1/2 Q, right? The charge of the experiencer is half of what it was. So that becomes the same as 2 times F over Q. Does that make sense? No, we're cutting the charge in half, so it's going to be 1/2 Q, right? So that makes my field twice what it was before, 2 times my original field. Does that logic make sense? The problem is there's a mistake with that. That's exactly what I was going to do at first, not because I wanted to illustrate a mistake, but because I was thinking that's what we were going to do. But then as I started it, something struck me. We're talking about the experiencer here, right? Let's go back to gravity for a second, because we have a little bit of an easier time visualizing that. Let's say that Dylan is experiencing the gravitational field strength right there at his desk. What's the strength of that gravitational field? 9.81. Now let's say that some Japanese sumo wrestler comes in, replaces Dylan. What's the gravitational field experienced by that sumo wrestler? 9.81. The experiencer doesn't affect what the field is. Does that make sense? So what's the answer to C? If the magnitude of the test charge is in the field is halved, what happens to it? Nothing, because the experiencer has no effect on it. Does that make sense? Okay. So the mathematical technique that we used here assumes that that field is going to be affected by that charge, but it isn't. Here's fundamentally the flaw in what we just did mathematically. We said that the charge gets cut in half, right? It does. It does. So mathematically, it should work out to be 2 times the original field. The problem is, when the charge gets cut in half, the force also gets cut in half. It just doesn't say that in the question. So if we want half F over a half Q, what would we end up with? Halves would cancel, and I'd end up with just whatever my original field strength was. Wouldn't change. Okay, does that make sense? So this seemed to make some logical sense, but when we take a step back from it, it's like, wait a second, it's not right. The field is not affected by the test charge or by the experiencer, only by the producer. Okay. Next question. Number 8B. A small test sphere or experiencer with a negative charge of 2.5 experiences a force of magnitude 5.1 times 10 to the minus 2 when it's that far from another larger sphere. Find the magnitude and the sign of the charge on the larger charged sphere. Let's copy this over so we have a little bit more space to work. Let's draw it out here. We've got this small test sphere with a negative charge. We're going to call it negative 2.50 times 10 to the minus 6 coulombs. It experiences an electrostatic attractive force (5.1 times 10 to the minus 2 newtons to the, we'll say it's to the left, when it's placed 0.0400 meters from another large sphere. So far, so good? Let's do A and B while we're at it, okay? Let's find the magnitude and the direction of the electric field at this point. If we're trying to find the field strength right there where that negative charge is that negative charge producing or experiencing it? Is it at the field or somewhere other than where the field is? It's at the field, right? So it's an experiencer, as Jared just said. So let's do A by using the experiencer equation. E is equal to F over Q. We got F, and we've got Q. We drop the sign of that Q. What do we end up getting for that? 5.1 divided by 2.5. 2.04 times 10 to the 4 newtons per coulomb. So there's my answer for question A, the magnitude and the direction of the field at this point. Now, question B, we want to find the magnitude and the sign of the charge on the larger charged sphere. Well, that larger charged sphere is going to be the producer. It's what's causing the field over there at that negative charge. So let's use the producer equation now. E is equal to KQ over R squared. We're trying to find Q. Let's rearrange it. Q is equal to E times R squared over K. Do we know what the value of E is? The field experienced by the negative was caused by the positive. So the field that we're going to use in question B is the one that we just found in question A, 2.04 times 10 to the 4. We've got R, don't forget to square it, 0.0400 squared. And of course, K is that constant. Do the math. Okay, I don't really care what we get there. Okay, you can do the math on that. How do we determine whether it's positive or negative? Well, if a negative experiences a force to the left, which way is the field? It's a good question. If the negative particle experiences a force to the left, which way does the electric field does it have to be? To the right. If the field is to the right, caused by that big producer, then what kind of producer is it? What kind of producer causes a field that goes away from it? Positive. So whatever the charge is, it's got to be positive because the field points away from it. Let's take a look at our last one, question 9B now. This is a tough one. This is pretty similar to a question that you had last Thursday and that you had to do for Friday. I wasn't here on Friday. I ended up showing you a little video of how I solved question B, or how I solved the question that I assigned on Thursday. Real similar to this one, except that that one was dealing with forces. This one is dealing with fields. I'm going to copy this over again so we have more space, and then we'll take a look at it here. We get a negative charge of 3 millicoulombs. First of all, I want to circle that millicoulombs because those are non-standard units, and I don't want to forget to convert those. This charge of 3 millicoulombs is negative, We'll call this charge 2, by the way. Negative 3.00 times 10 to the minus 3 coulombs. It's 1.2 meters to the right of another one. So my other one's going to be over here. And it has a charge of negative 2.00 times 10 to the minus 3 coulombs. They are 1.20 meters apart. I want to find a point in here somewhere where the field strength is 0. Now, I'm drawing it about halfway across. It's not going to necessarily be halfway across. We've got to figure out what that point is. Okay, I don't know where exactly to draw it. I just know it's going to be in between there somewhere. Let's do this. Let's call this distance r. The distance from 1 to point x, where the field strength is 0, is r. If the distance from 1 to x is r, then the distance from 2 to x is 1.2 minus r. Let's think about this logically. Okay? This plus this must be this. When we add r plus 1.2 minus r, then what do we end up getting? 1.2. So this is correct. (1.2 minus r and r). Now, let's do our next thing here. Let's say that the electric field strength caused by number 1 has got to be the same magnitude as the electric field strength caused by number 2. It does. And that's not a rocket science piece of information, I don't think. In the end, if the net field has got to be 0, they've got to balance each other. One's got to be to the right, one's got to be to the left. And in fact, that's exactly what it is. The field caused by number 1 is to the left. The field caused by number 2 is to the right. And they've got to be the same value, otherwise they wouldn't balance each other. The field caused by number 1 is going to be given by the equation kq1 over r squared. Right? K times q1 over r, the distance that separates 1 and that point where the field strength is 0, x, is r. The electric field caused by number 2, well, it's going to be equal to k times q2 over, what's the distance between x and charge 2? What's this distance right here? 1.2 minus r. Don't forget to square that. Now, the k's cancel. You don't have to, because we know the number, but in the end, it's both the same. So if we want to simplify it, we can cancel it. We can FOIL this if we want. If we FOIL this 1.2 minus r, it'll work out. It comes a little bit ugly if we do that. There's an easier way. We can do the same thing to both sides. Do whatever we want as long as it's the same. We can multiply both sides by 16,134.21 as long as we do it to both sides. Or we can just square root both sides. If we square root both sides, then we end up with the square root of q1 over r equals the square root of q2 over 1.2 minus r. We've just gotten rid of the square. Now, we've introduced some square roots, but that's okay because we know the numbers that we can physically square root. Let's start plugging some numbers in now. q1 was 2.0 times 10 to the minus 3. So this is going to be the square root of 2.0 times 10 to the minus 3 over r equals the square root of 3 times 10 to the minus 3 over 1.2 minus r. Let's get some numbers here. Simplify this even more. Let's say the square root of 2 times 10 to the minus 3 is 4.4721 times 10 to the minus 3 over r equals the square root of 3.0 times 10 to the minus 3 gives me 5.4772 times 10 to the minus 3. over 1.2 minus r. It's a little bit simpler here. Now what I'm going to do is cross multiply so that the r's go up to the top. Okay, this r goes up this way, this goes up this way. We get 4.4721 times 10 to the minus. Hey, just noticed another little shortcut. Just notice this. Can I cancel that 10 to the minus 3? It's on both sides. Why not? So it becomes 4.4721 times 1.2 minus r equals 5.4772 times r. It's even better looking now. Still not pretty, but it's even better looking. Let's take that 4.472 over to the left side, to the right side, I should say, by dividing. Could you have crossed out the 10 to the minus 3 what was under the square root? That's a good question. Intuitively, I would have said yes, but I'm not comfortable with that. So I wouldn't have done that. I guess the rule of thumb for me is if I'm not sure if I can cancel it out, I won't. So I would leave it. I would leave it. I'd have to look at that a little bit more closely to see if you could mathematically get away with that. You can definitely do it here. But again, if you're not sure about that, if you're not sure if you can do it here, just don't do it. Because it's still going to work out for you, right? Okay, yeah, sounds good. All right, so we get 1.2 minus r equals 1.2247 times r. All right, we've just taken that 4.4721 over by dividing. So this is what we have. Now, listen very carefully. What's 1 apples plus 2 apples? How many apples do you have? 1 apple plus 2 apples is 3 apples. What's 1r plus 2r? 3r. What's 1r plus 1.22r? 2.22r. So we're adding apples, we're adding r's. It doesn't really matter. I want to take this r over to the other side. Since it's a negative on the left side, I'm going to take it over by adding. It becomes 1.2 equals 2.2247r. Right? It's 1.22r plus 1r. Now it's easy, right? Now it's just 1.2 divided by 2.22. We end up with 0.539. So that point that has 0 electric field strength is 0.539 meters to the right of charge 1. And we could figure out what it is on the left of charge 2 by just taking that number and subtracting it from 1.2. Now, is this a question that's likely to appear as a multiple choice question on a test? Probably not. Probably not. Question number 1 is absolutely fair game. Question number 2, that's a tough question. And that's too long of a question in my mind to go on a multiple choice exam as well. It just takes you too long when it's a multiple choice question. I don't expect you'd see something like that. You never know. But I'd be very, very surprised if you did. Okay, look, if you do, great. Now you've got some kind of little bit of a leg up on doing it. If you don't, it's not a waste of time. If you work through it, your mind has grown a little bit so that the other questions look a little bit easier now. What I'd like to do at this point is just have you work on a couple of quick multiple choice questions. 44 is the first one. I'll give you about 30 seconds to do that, and then there's one more question that should go real quickly for us as well. All right, let's take a quick look at this one. 44. Who votes A for this one? A, B, C, D? Okay, most people voted for A. Is it negative and negative? Well, the shape tells us that they're two like charges, right? If it was opposite charges, positive and negative, then the shape wouldn't look like this. What tells us that they're both negative as opposed to both positive? Dylan? Good. So the shape tells us they're both the same. The arrows tell us that they're both negative. Good. So the answer is, in fact, A for that. Take a quick look at question 46 here. See what you can do with that over the next 30 seconds, and then that'll be it for the day. Okay. Let's take a look at this one. How many people said A for this one? B? C? D? Okay, most people are voting for B, toward the left of the page. The field caused by the first one is towards it, right? Always points towards a negative producer. The field caused by charge 2 is away from it, always points away from a positive producer. When we add these up, regardless of whether we know what the numbers are or not, when we add these up, the net field is going to be to the left, so the answer is going to be B, toward the left. Here's your homework for tonight. Worksheet number 8, questions 1 to 9. There are, I think, 12 questions on that worksheet, so I'm being extra nice to you today by only giving you the first 9 questions. You see what you can do with those, and we'll look at them tomorrow.